We spend a lot of time modeling mechanical systems in this course. Generally, the more complicated the system, the more complicated the mathematics. Have a look at this. It's an air puck connected by a spring to a pivot here. We can model the system as a particle connected by a perfect spring to a fixed point. Now, if we're just considering the one-dimensional motion like this, I'm sure you'd be able to solve the problem. But what happens if I set it going like this? Well, that looks a bit more complicated. And even for the case of a perfect spring, the equation of motion cannot be solved analytically. But there's something special about this system which will allow us to find out quite a lot about how it moves without having to solve any equations of motion. You see, the force on the puck is always along the line connecting the puck to the peg here. It's an example of what's called a central force. And in this program, we're going to develop methods for analyzing the motion of particles moving in 2 or 3 dimensions under the influence of central forces. But the first question to ask is, what do we mean by a central force? Well, a central force is one that's always directed towards or away from a fixed point, which I'll make the origin for convenience. So let's have a look at this particle, which is moving under a central force. First, let's draw in the position vector of the particle. Then the force on the particle will always be along the line of that vector. So here, it could be directed this way, and here, it could point towards the origin. At any position, it can be either directed this way or this way. But the important thing is it's always directed along the line of the position vector. So I can write the force as g of r times r, where g is a scalar function which depends on position. So, is there anything we can say about the motion already? Well, in fact there is. And that involves thinking about the angular momentum of the particle. So, what is its angular momentum? Well, at any instant, the angular momentum L is found from the position vector r and the velocity vector r dot. In fact, L equals r cross m r dot. And because L is the cross product of two vectors, this tells you that L is always perpendicular to both r and r dot. What does this equation tell you about how L varies with time? Well, to find that out, you need to differentiate it. The right-hand side is a product, and using the product rule gives you this. But mr double dot is just equal to the force. And because we're dealing with a central force, that's just g times the vector r. So I've got two terms on the right-hand side, which are both cross products of identical vectors. And a vector crossed with itself is just 0. So both terms are 0. So L dot is 0, which means that the angular momentum is a constant. In other words, angular momentum is conserved for motion under a central force. Now we're going to assume that L is not the 0 vector. We'll leave that special case for the program notes. So, what does this imply about the motion of the particle? Well, from the definition, r is always perpendicular to the angular momentum vector L. And if L is a constant, that means that r must always be in a plane. We can call this plane the xy plane, and that choice means that L is parallel to the z-axis.
So motion under a central force always takes place in a plane. But so far we've used only half the information we've obtained about the angular momentum. If the angular momentum vector is constant, not only is its direction constant, its magnitude is constant too. What can we deduce from this? I can write L as a scalar multiple of a unit vector, which I'll call k because we're aligning the z-axis with the direction of L. Then the multiplier, Lz, is a constant. But you've already worked out the angular momentum of a particle of mass m moving in a plane in terms of polar coordinates. it's m r squared theta dot times k. So we deduce that r squared theta dot is a constant. In fact, it's Lz over m. This result, that r squared theta dot is constant, is very useful when you're analyzing motion under a central force. You see, if you express your equations of motion in terms of polar coordinates, there will be 3 variables involved. That's r and theta, of course, and also the time. And the fact that r squared theta dot is constant allows you to eliminate one of these variables. We'll be using this trick later on in the program. One important case in which our methods apply is the motion of a planet about the sun. The gravitational attraction of the sun can be treated as a central force. Now, the fact that r squared theta dot is constant for planetary motion was discovered from observations by Johannes Kepler at the beginning of the 17th century. As the particle moves, its position vector sweeps out areas. What Kepler said is that the rate at which the position vector sweeps out area is constant. In other words, equal areas are swept out in equal times. So the area law, which Kepler discovered for planetary motion, is actually true for motion under any central force. That's because it's equivalent to the fact that r squared theta dot is constant. Well, before we go any further, let's summarize what we've discovered so far about central forces. We've defined what a central force is, and we've shown that for a particle moving under any central force, angular momentum is conserved. And that's allowed us to say 2 things about the motion. Firstly, that the motion takes place in a plane. And secondly, that r squared theta dot is constant. And that can be expressed geometrically as the area law. And we've deduced all this without solving any equations of motion. Indeed, without even knowing anything about the magnitude of the force at all. So what happens if you do know something about the magnitude of the force? What else can you deduce about the particle's motion?
Well, it turns out that with one simple assumption about the magnitude of the force, you can make a lot more progress in understanding the motion. So, let's look at the magnitude of a general central force. At any point, I can draw an arrow representing the force and make the length of the arrow denote the magnitude of the force. At another point, both the direction and the magnitude of the force will have changed. And if I carry on drawing the arrows, you can see how the strength of the force varies over the xy plane. A clearer way of showing this is to draw curves connecting points where the force strength is the same. These are the contour lines, or level surfaces, of the magnitude of the force. For a general central force, there isn't anything special to say about these lines. But what about this central force? The strength of the force is the same for all places the same distance from the origin.
A central force for which the magnitude of the force at each point depends only on the distance of the point from the origin is called an isotropic force. And for the rest of the program, we'll be considering isotropic central forces. Now we can express a general central force like this, where ER is the unit vector in the radial direction. But if the force is isotropic, then F is a function of distance alone. The important thing about an isotropic central force is that it can be derived from a potential energy function, and in a particularly straightforward way. For such a force, you can always find a function u, which is itself a function of distance r, such that f of r is minus du by dr. And in fact, du by dr times er is the gradient of the scalar field u. And so u is a potential energy function for the force. So we can define the total energy of a particle moving under an isotropic central force. It's the kinetic energy plus the potential energy, as we've just described. And the total energy is conserved. This is true for any isotropic central force. The kinetic energy is a half mv squared, and the potential energy is u. But we're still dealing with a central force, so I know that the motion is in a plane. So I can write down the velocity v in terms of polar coordinates. It's r dot er plus r theta dot e theta. ER and E theta are the polar unit vectors. They're orthogonal, so V squared is just the sum of the squares of these coefficients. And that gives me this formula for the energy. I've now got an energy equation with r and theta in it, and also the time, because of the dots. But remember that I can use the conservation of angular momentum to eliminate one of these variables. I'm going to eliminate theta. And when I do so, I get this equation. Now I have one term here involving r dot, and two terms involving just r, which is natural to group together. What I'm left with is very like an energy equation for one-dimensional motion, with this as the kinetic energy term, and this as the potential energy term. I'm going to take advantage of this convenient coincidence, but I'll have to keep in the back of my mind that I'm really dealing with a two-dimensional problem. I've suppressed information about theta, and a half mr dot squared isn't really the particle's kinetic energy, only the radial part of it. However, let's proceed as though we were dealing with a one-dimensional problem, and call this the effective potential, U effective. And a good way of using this to deduce things about the motion is to draw the graph of U effective. So suppose the graph of the effective potential looks like this. Now the total energy is constant, and it's determined by the initial conditions. So let's draw on a horizontal line to represent that total constant energy. But the total energy is the sum of two terms, the effective potential and a half mr dot squared. So when the particle is here, the difference between the line of energy and the graph of U effective represents the term in r dot squared. As the radial distance of the particle increases, a half mr dot squared gets smaller, until the graph of U effective reaches the line of E. For that value of r, a half mr dot squared is 0. So the radial speed must be 0. And because r dot squared can never be negative, the particle cannot move beyond that point. Similarly, when the particle is here, the radial speed is also 0. In fact, motion is possible only where the total energy line lies above the curve. So the values of r at the left and right of the energy line are turning points of the radial motion. They're the points where the particle is closest to and furthest from the origin, and it will never move beyond those points. But remember that we're really talking about two-dimensional motion here. What does this imply about the motion of the particle in the plane? Well, the two turning points define two bounding circles for the motion. And even though you can't describe the exact path of the motion, you can determine these bounding circles. But what happens if I change the total energy? Well, that just changes how high up the energy line is. And all that affects is the position of the turning points. For graphs of U effective like this, provided the total energy is above this minimum value, there are always two turning points. And so there are always two bounding circles for the path of the particle. In this case, we say that the path of the particle is bound. But what happens if the graph is like this? Down here, the motion has two turning points and the path is bound as before. What about up here? What happens if the total energy is as large as this? Well, here's the graph of U effective again. This time, there's only one turning point, and the particle can never get closer to the origin than this. But there's no limit to how far away from the origin it can get. So what does this imply for the two-dimensional motion of the particle in the plane? The path has an inner bounding circle, but no outer one. And this time, the radial distance increases indefinitely. Paths of this type are called unbound paths. Looking at energy diagrams for isotropic central forces allows you to find the bounds of the motion, if there are any. Let's see how that allows us to analyze motion under a particular force, the puck we saw earlier.
Now you know that the puck is moving under a central force, but is it an isotropic force? Well, the force on the puck depends on the extension of the spring, and that in turn depends only on the length of the spring. In other words, how far away the puck is from the central peg. So this is isotropic. Now you know the motion is pretty complicated, but if I look at the graph of the effective potential, I can determine if there are any bounds on the motion of the puck, and if so, what they are. The effective potential energy is the sum of two terms, a 1 over r squared term and the true potential energy of the spring. For a perfect spring, the potential energy is quadratic, so the graph looks like this. The graph of 1 over r squared looks like this. And adding the two graphs together gives me the graph of U effective. I can see from this that whatever the value of the total energy, there are going to be two turning points to the motion, which means the path of the puck is going to be bound. So let's look again at the experiment. I'll set the puck going. And now watch the path of the puck being traced out. The path is contained in a ring bounded by an inner circle and an outer circle. So, even though I haven't made any attempt to describe the motion exactly, I have got useful information about it using conservation of energy. So now, let's stop again and take stock of what we've discovered so far about isotropic central forces.
Well, an isotropic central force is just a special kind of central force. And so all the things we said about the conservation of angular momentum still hold. But for an isotropic central force, there's another thing that's conserved, the energy. By using the graph of the effective potential energy, I've been able to say two things about the motion. Firstly, whether the motion is bound or unbound. And secondly, if it is bound, I can determine the closest and furthest distances of the particle from the origin. And again, we've deduced all this without having to solve any equations of motion, and without even knowing the force completely. In the last part of the program, we'll see how this information can be used to describe the motion of systems where we do know the magnitude of the force. Tom.
In fact, we'll be looking at two forces which are very similar, but which are used to model very different phenomena. And you've already met the first of these in the unit, the force of gravity. According to Newton's law of universal gravitation, the force due to gravity is inversely proportional to the distance squared. And you've also seen that that gives rise to a potential energy function, which is inversely proportional to r. And gravity is an attractive force, so it's directed in the negative ER direction. So mu is always negative. But there's another force in nature that obeys the inverse square law, and that's the electrostatic force between charged particles. In electrostatics, each charge can be positive or negative. But I'm going to deal only with the case when both charges have the same sign. In this case, the electrostatic force is repulsive. That is, it's directed in the positive ER direction. So mu is positive. So I've got two forces, both inversely proportional to r squared, but one attractive and one repulsive. How do the motions compare and differ? Well, both forces are central forces, so I know the angular momentum is conserved. So that tells me that in both cases, the motion is in a plane, and that r squared theta dot is constant. And I also know that both forces are isotropic, because they depend only on the length of the radius vector r. So I know energy is conserved too. And I can look at the effective potential energy to see if there are any bounds on the motion in each case. I'll do that now. Well, remember, U effective is the sum of two terms, a term in 1 over r squared, and a term that's the true potential energy of the force. In both these cases, the true potential energy is just mu over r. So now I can draw the graphs of U effective in each case. But how's the sign of mu going to affect the graphs? In the gravitational case, U effective is formed from a 1 over r squared graph. to which is added a minus 1 over r graph. For small r, the 1 over r squared term dominates, and for large r, the 1 over r term dominates. And the result looks like this. So, what can you say about the bounds of the motion? Well, in fact, you've seen this graph already in the program. For low energy levels, the motion is bound. That's true of planetary orbits, which are ellipses, but for higher energy levels, the paths can be unbound. But what happens in the electrostatic case? Well, let's see what U effective looks like in that case. As before, the first term is a 1 over r squared graph. But this time, the other term is positive 1 over r. Both graphs are positive for all values of r. And the resulting graph of U effective looks like this. This time, there's no possibility of bounded motion, and that's what you might have been expecting from a repulsive force. So, the difference in sign between the two forces leads to very different graphs of U effective. Now, how does the motion in the electrostatic case relate to unbound motion under gravity? Well, if you consider the case of unbounded motion under gravity, the path you get is like this. It's called a hyperbola. And for the attractive force of gravity, the particle hooks around the center of attraction at the origin. But what happens in the electrostatic case? Well, it turns out that you get exactly the same curve, but with a different relation to the origin. In this case, the force is repulsive, and the moving particle is deflected away from the origin before it reaches it. For different values of L and E, you get different shaped hyperbolae. In 1911, the physicist Ernest Rutherford published results of experiments that showed that the positive charge of an atom is concentrated in a very small, massive nucleus at its center. In these experiments, he fired other positively charged particles at the atoms and showed that they followed unbound orbits, just as predicted by the classical theory of particles, repulsed by a force in the way we've just shown. He found that some of these particles were so strongly scattered that their hyperbolic orbits took them almost back along the way they came. This particular result could never have been explained by the other competing theories of atomic structure. It was, he said, as though you had fired a 15-inch shell at a piece of tissue paper and had it bounce back and hit you. He thus gave a powerful case that this is the sort of model that represents atoms: a massive, concentrated, positive charged nucleus surrounded by orbiting electrons. Actually, the modern theory of quantum mechanics modifies this model somewhat, especially with regards to the way one should visualize the so-called electron cloud around the nucleus. But many features of this classical Rutherford model do carry through in an almost magical way.